A small sample hypothesis test continued. Example 5a. In a sample of n equal 4 tosses of a coin, the proportion of the heads was p hat 3 out of 4, or 3 divided by 4 is 0.75. If the coin is evenly weighted or fair, the proportion of heads in the long run would be p0 equal to 0.5. If the coin is evenly weighted, it should turn up heads half the time and tails half the time. We want to test the following hypotheses at the alpha equal 0.05 level of significance. H naught or H0, P is equal to 0.5, the coin is evenly weighted, versus HA, P not equal to 0.5, the coin is not evenly weighted. And we want to first check to see whether n times P0 and n times Q0 are both at least greater than or equal to 5. So n times P0, our sample size n is 4. P0, that's the value of P if the coin is evenly weighted, 0.5. 4 times 0.5 is 2, and that's not greater than or equal to 5. Okay, and then we could also do n times 1 minus P0. 1 minus 0.5 is also 0.5, so it's going to be 4 times 5. Again, that's 2, and that's another no. In order to use the shortcuts with the z-table, we would have to have a yes, yes. If we have a yes, no, or no, yes, or no, no, then we have to use the exact binomial probabilities, and usually we'll be doing that with a tree diagram. And because we have a two-sided test, we want to compute the probability of either extreme. So we want the probability of that our sample proportion is 3 out of 4 heads. We want the probability of either at least 3 out of 4 heads or at least 3 out of 4 tails. The full tree diagram would have 16 paths. Just for convenience, I'm only going to show the paths for which either the proportion of heads is at least 3 out of 4 or the proportion of tails is at least 3 out of 4. Okay, so I'm going to draw the tree as if H naught is true. So if H naught is true, we have a 0.5 chance of a head, 0.5 chance of a tail. And because all these probabilities are 0.5, we don't have to really put them in the tree. We can just okay, so this is the first toss. It's either a head or tail. And then the second toss is also either a head or a tail. So we have, with two tosses, we have 4 possibilities. We have head, 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 tail, tail, head, tail, tail. And there's, once we have 2 heads, let's see, okay, but, well, let's do this again. So, okay, so third toss, again, either head or tail. A head or tail. I'm kind of running out of space here. And that'll give us 8 possible outcomes. That's the third toss. The fourth toss is, again, either head or tail. Head, tail. Now we don't really need to put all the paths in for this fourth toss. We already have 2 heads and a tail here along this path. The only way we're going to get 3 of the same is if it's going to be 3 heads. So we're not going to get 3 tails. So it's going to be we only need to show the paths where we have either at least 3 heads or 3 tails. Likewise with this third path here, we already have 2 heads and 1 tail. The only way we're going to get 3 of the same is if this fourth toss is a head. This path here, we have a head and 2 tails. The only way we're going to get 3 of the same, it would be if the last toss is a tail. So we don't have to write out all the possible combinations. Here we have 2 heads and a tail. The only way we're going to get 3 of the same would be 3 heads. Tail, head, tail. The only way we'll get 3 of the same is if this passes as a tail. Tail, tail, head. So this has to be a tail. And then tail, tail, tail. We could have either a head or a tail here. To still get 3 of the same. So this is the fourth toss. So fourth toss, actually there's 16 possible outcomes, but 1, 2, 3, 4, 5, 6, 7, 8, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we only have 10 that we need to count here. Okay, so each of these probabilities are going to be the same. It's probability of a head is 0.5, the probability of a tail is 0.5. So I didn't write in all the probabilities here. These paths will all have the same probability. 0.5 times 0.5 times 0.5 times 0.5 will be 0.0625. So all of these are going to be the same. 0.0625, 0.0625, 0.0625, 0.0625, 0.0625, 0.0625, 0.0625, 0.0625, 0.0625. Okay, so the total is going to be the p-value. We have 10 numbers. 0.0625 times plus itself 10 times be 0.625. So that's our p-value. So that's a pretty high p-value. So that means there's little or no evidence against H naught. So the based on a p-value of 0.625, if we compare it to alpha, oftentimes the level of doubt is taken to be 0.05. That's established by the researcher, and not all researchers specify a level of doubt, but anyway, the level of doubt is expressed by the Greek letter alpha, lowercase alpha, and so our p-value is more than alpha, and so we fail to reject H naught. The sample does not provide enough evidence. 0.6 is between 0.1 and 1. The sample provides little evidence that the coin is unevenly weighted. There's a 60. Even if the coin is evenly weighted, there's still more than a 60% chance of getting 3 out of 4, either getting 3 out of 4 heads or 3 out of 4 tails. Okay, so this diagram, I've shown this in other videos, the same diagram here. It's a diagram that sort of helps us to understand the types of errors that could happen, or the possible outcomes. Either H naught is true or HA is true, and either we don't reject H naught or we reject H naught. And 2 of these possible outcomes are errors. So we have 4 possible outcomes. We can reject H naught. We could fail to reject H naught if H naught is true. We could reject H naught if H naught is true. We could fail to reject H naught if HA is true. We could reject H naught if HA is true. So 2 of these are errors. If we reject H naught when H naught is actually true, that's called a type 1 error. If we don't reject H naught and HA is true, that's a type 2 error. So alpha is our desired level of a type 1 error. That's often established by the researcher. some researchers would use 0.01 or 0.05. It's it represents the how accurate we would like the results to be, or how strong we want the conclusion to be. So if you want to be very, very sure of your results, then you make alpha very small, so you have a small probability of a type 1 error. So in this case, we'll usually take alpha to be 0.05 or 5% chance of a type 1 error. So anyway, in this case, our p-value of 0.6 is more than alpha, so we reject H0. So it's possible we would have made a type 1 error in this case. By rejecting H0, it might be that the coin is actually unevenly weighted, but we had a small sample. We said it didn't provide enough evidence, and so we it's possible we would have made a type 2 error here because we didn't reject H0. So it's possible it really is unevenly weighted, but we didn't reject H0, and it's possible we would have made a type 2 error. We can also make it represent these paths of the tree diagram in a table. I did a tree diagram, but you can also do it in a table. You have to list all the possible sequences with either at least 3 heads or at least 3 tails. So we have 4 heads here. We had 3 heads and a tail. 2 heads and a tail and a head. A head, a tail, and 2 heads. Head and 3 tails. A tail and 3 heads. We have tail, head, tail, 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 head, tail. So you have to see which one's missing. What we don't have here is a head followed by 3 tails. So I left one blank here, but we do have a head followed by 3 tails. Let's see. No, we don't have 3 tails followed by a head is what we don't have. We have 2 tails and a head, 1 tail and a head, tail, head. So 3 tails followed by a head is what we don't have. So that's the missing path here. And the probabilities are going to be the same as 0.5 times 0.5 times 0.5. 0.0625. Okay, so that was the missing path. Okay, so if we have, if that's 3 out of 4, suppose we flipped the coin 4 times instead of 3 out of 4 heads, we had 4 out of 4. So then, in this case, we'd only need, there's only 2 paths to the tree that we would need to make. We want at least 4 heads or at least 4 tails. So we don't really need the full tree. Again, the full tree would be 16 paths, but we only need the paths where we either have 4 heads or 4 tails. So the probabilities are all 0.5. You don't really have to write them down because they're all the same, but I'll write them down here. And if you multiply straight across, 0.5 times 0.5 times 0.5 times 0.5, 0.0625. And then the total, or the p, which would be the p-value, would be 0.125. If you want to put a 0 on the end, you can. But this is still not enough evidence to say the coin is unevenly weighted. So it's still more than 0.05, and it's actually even more than 0.1. So it's little evidence. Sample provides little evidence that the coin is unevenly weighted. Maybe it is, maybe it isn't. We don't know. If, when we fail to reject H0, we don't know whether H0 is true or not. We just say that there's not enough evidence to say either way. We could now, if the sample proportion was 6 out of 6, you've got flipped it 6 times and got 6 heads. Now we're going to have again, we want to do only the extremes. So either the two-sided test. So we want to do either compute the probability of having either 6 heads or 6 tails. So it's going to be 0.5 times 0.5 times 0.5 times 0.5, or 0.5 to the 6th power. That's going to be 0.0156. 15625. And then the total would be the p-value. .03125. Okay, so that's so in this case it's moderate evidence. So if we go back to our chart here, we have p-value of 0.03, and that would provide moderate evidence that the coin is unevenly weighted. 0.03 is between 0.01 and 0.05, so it's moderate evidence. So if our standard is alpha equal 0.05, that would be enough to reject H0 and conclude that the coin is unevenly weighted. So this is moderate evidence coin is not evenly weighted. When we start getting six heads in a row, then it start to look like, well, maybe the coin is not evenly weighted. 4 heads in a row is not so unusual. Okay, so that concludes this presentation.